Okay, geometry, we are on lesson 2. So, unit 5, lesson 2, similarity and transformations. Warm up. List all the types of transformations we have talked about this year. So, these are the transformations. We have had reflections. We have had which is a flip. Remember, we used that word as well. We have rotations. Why aren't we drawing? Rotations, which are turns. We have translations. I'm not really sure why I'm having writing problems, but then okay, translations, which are slides. And then finally we had dilations, which were when we would shrink or enlarge. And if you can remember, when we talked about translations, I think this is unit 2 maybe? Reflections, rotations, and translations all were congruence ones. So these and this one made congruent figures. These were congruence transformations. But dilations shrunk or enlarged. So they were not congruence. They are similar transformations. So the shapes are similar, but they are not congruent. And that's what we're going to focus on in this unit. So example 2, graph the following two triangles. So in triangle ABC, we have A is at 2, 1, A. B is at 2, 3, B. And C is at 5, 1. And there is that triangle. Then we have triangle DEF, which is at 4. Oh, I'm going to get another color. All right. We have 4, 2. Oh, my. Sorry, guys. Not sure what's going on here. Okay. So try that again. We are at 4, 2, which is D. 4, 6, which is E. And 10, 2, which is F. And so we have these two triangles. And this would be a dilation. If we start with ABC, we got bigger and turned into DEF. These two triangles are similar. They are not congruent. Just a reminder, similar means congruent angles, proportional sides. Similar means same shape. That's from the angles, different size. Whereas congruent from last unit means congruent angles and congruent sides. Everything the same. So you have to keep these separate. All right, what type of transformation occurred when you graphed ABC and DEF? Well, I already told you, those are similar. Which means the type of transformation, though, is a dilation. That would be the proper answer there. A transformation that produces similar figures is a similarity transformation. Another word for that you need to know would be a non-rigid transformation. We use the word rigid for these other three. Congruence transformations are also rigid transformations. Rigid. So reflections, rotations, translations. Those are rigid. Dilations are non-rigid. Make sure you know that word because that's going to pop up. The only similarity transformation is a dilation. And remember, a dilation can go smaller or bigger. So it can be a shrink or it can be an enlargement. We call them all the same. They're called dilations. All right. So representing transformations in the coordinate plane. Remember, our rule for a dilation is really nice. We have this k value, and all we do is we multiply that k value by both x and y. So here we're saying k is greater than 0. Now if k is less than 0, then k, that means k is a negative number. And so let's say, let's pretend k is a -4. So that negative portion makes it a reflection. And then the 4 portion is the dilation portion. Okay, so when you have a negative number for that k that you're multiplying, then really technically you're doing two things. You're doing both a reflection and a dilation. Okay, example question. A polygon has the vertices D, -8, 0, E, and F. Graph the pre-image and image after a dilation with a scale factor of 1/4. So since my scale factor is 1/4, so if k is less than 1, which means it's a fraction, but still greater than 0, then basically we're going to shrink. We're going to get a smaller shape, right? And if k is greater than 1, then we're going to enlarge. So in this case, we know our image. This is our image. Remember, over here's the pre-image. What we start with is the pre-image, and what we end with is the image. And so the pre-image is going to get smaller if I multiply by 1/4. Whereas the image will get bigger if I multiply by a number greater than 1. All right, so in this case, every number gets multiplied by 1/4. But before we do that, let's first graph D, E, and F. So D is -8, 0. Oh my goodness. It's going to take a while if it keeps jerking. Okay, -8, 0 is right there. There's D. -8, -4 is right there. That's E. And F is -4, -8. So I have this triangle. Get another color going. All right. So now I'm going to find that is the pre-image. I have graphed the pre-image. The image is I take this and I multiply everything by 1/4. So the rule here is 1/4 x, 1/4 y. By the way, if I ask for the rule, this is what you write. Here's the rule. Okay, so that's what I'll be doing. So 1/4 times -8 is -2, 0. -2, -1, -1, -2. All right, so graphing that, I have -2, 0 for D prime. I should have written that somewhere else. Hold on. Get rid of that. Okay. I have -2, 0 for D prime. I have -2, -1 for E prime. And I have -1, -2 for F prime. Look at how tiny my triangle got. So when I have a scale factor, when k, like I said up here, when k is less than 1, so it's a fraction, you're shrinking. And so you always should check your work, make sure that you shrunk when you multiplied by 1/4. The shape should be the same. It's the size that will change. All right, moving on. Question 5. Determine whether ABCD, careful there with the order, is similar to JKLH. So that order tells you what has to go together. If they are similar, list the ratio of the side lengths. So the first thing we want to do is if they are similar, then we have two requirements. One, angles. What is going on? I seem to be having some technical difficulties. Well, I like that purple color. Let's go back to that. Okay, angles congruent. And then the second requirement, because we're trying to find out if they're similar, the second requirement to be similar is sides proportional. All right, so let's first check our angles. So in this, we have angle A has to go with angle J. So this angle is a right angle, this angle is a right angle. Because whenever you have horizontal and vertical lines, you get a right angle. And so we can say angle A is congruent to angle J. And then we can say C has to go with K. So C is over here, 90 degrees. K is right there, 90 degrees. So I can say angle C is congruent to angle K. D goes with L. So D is right here, L is right there. Those are both made by vertical and horizontal lines. So angle D is congruent to angle L. And then finally, B and H, both 90 degrees as well. So angle B is congruent to angle H. So we met the requirement for the angles. Now we need to do the sides proportional. So when you do that now, make sure that you are going with corresponding side lengths. So the first one is AC, that goes first, and JK. So let's just compare. I'm just going to choose to have this be in the numerator, this will be in the denominator. So the big number will be up top, the small number will be down on the bottom. You can do it the other way if you want, but AC to JK. So from A to C, you can count those because it's horizontal. You could use the distance formula, but counting would be kind of nice here. And you go 9. And so AC is 9. JK, again, it's horizontal, so you can count and you get 3. That simplifies to 3. Let's do the next set of sides, which would be CD to KL. So CD to KL. Notice I'm consistent with the big sides of the triangle in the numerator. I just need to be consistent here. CD. So going from C down to D, we are getting 9 again. So, and KL, counting that, will be 3. And so we get 3 again. And you can already see that these are going to be similar, but we're just going to go through. Next, we're going to do DB to LH. So DB again is from here to there, which is 9. LH is 3. So we get 3. And then the last one is going to be A to B. Goes with J to H. Not J to K, J to H. And A to B is 9. And J to H is 3. So there we go. We have all of our ratios simplify to the same number, and all of our angles are congruent. So yes, they are similar. Yes, similar. And then it says, list the ratio of the side lengths. Well, the ratio is 3. Okay, moving on. Graph and label the 2 triangles listed below, then describe the transformation that is displayed in this graph. So first we need to graph them. So I'm assuming that we want triangle here of ABC. We want triangle here of A prime, B prime, C prime. So triangle ABC is 1, 2, 2, 2, and 1, 3. So A, B, C is this tiny little triangle. Doing the other one, we have -3, -6, 2, 4, I think that's 6, wait, 2, 4, there's 6. There's A prime, -6, -6, there's B prime, and then C is -3, -9, and there's C prime. So we have these 2 triangles. It says graph and label them, so we did that. It says describe the transformation that is displayed. So what did we do? Well, the first thing we did is we enlarged it. This is a tiny triangle, and it got bigger. What number did we multiply by to get bigger? Well, if you compare this, 1 times 3 gives me my 3. And then, of course, we have that negative. But let's just look at the numbers without the negatives first. Every one of these is multiplied by 3. And so we know we dilated by 3, right? So our rule, xy, is going to map to, I multiplied x by 3 and I multiplied y by 3. Now the second thing is that you notice that we flipped it, right? We flipped it over the x-axis, and actually we flipped it over the y-axis. And so that negative, which technically is a rotation, but that negative has to be in there. So we multiplied both of these by that negative, and that rotates it. If we took the negative out, we would have just had a bigger triangle right there. But we did it with the negative, so that also flips it. And when you flip 2 times, when I flip both x and y axes, that's called a rotation. All right, question 7. Determine whether the polygons with the given vertices are similar. So, first let's graph them. I'm not a big fan of yellow because you can't see it, so here we go. A is at 2, -1. B is at 3, -1. And C is at 3, -2, 3, 4. There's C, there's B, there's A, and we have this little triangle. All right, now we have P in another color. How about brown? I've never used brown. Okay, 4, -2. There's P. Q is 6, -2. And R is 6, -8. So what we have are these 2 little triangles. Hopefully on your paper you drew them neater than mine because they are similar. They look similar, don't they? But maybe not so much on my screen. But anyhow, okay. So our question is, determine whether the polygons with the given vertices are similar. Are they similar? Well, if they are, we have to prove it. So what do we need? We need 2 requirements. Requirement 1, congruent angles. Requirement 2, proportional sides. Okay. So the congruent angles, if you look at these, this angle right here, I'm just going to reason this out with you a little bit. This angle right here is vertical, horizontal, vertical, horizontal. So angle B is congruent to angle Q because those are both 90 degrees. Okay? Then angle R down here, if you would look at that neatly, the slope from this going straight down and going over there, that slope is up 3/1, up 3/1, which is the exact same slope from right here. Up 3/1, up 3/1. And so, therefore, these 2 angles and these 2 angles are also going to be equal. If you want, you could get out a oh my goodness, my mind is blank, a protractor to measure those. But what I want to, we are going to say all angles congruent because they all have the same slope from the same starting point. But now we need to prove our sides. And so looking at that, AB, which I've made a mess of, AB goes to PQ. And that's a horizontal line, and I can count that. So AB is 1, PQ is 2. All right. Next one, BC goes to QR. So I can count that. BC is 3. QR is 6. Yeah. Which also simplifies to 1/2. Look at there, we have the same proportion for both of those. But now we get to the interesting one, which is AC compared to PR. And so to do AC and PR, those are diagonals, and those we're going to use the distance formula. Do you remember the distance formula? Distance formula equals the square root of x minus x, like x1 minus x2 squared, plus y1 minus y2 squared, all under the square root sign. So for A, we have the square root of the coordinates for AC. I'm doing AC first. I'm going to go 3 minus 2 squared plus negative 4 plus 1 squared. All I'm doing is subtracting my x values for A and C and my y values for A and C. And then for PR, I'm going to do the same thing, but I'm going to subtract my P and R x and y values. So I have 4 minus 6 squared plus negative 2 plus 8 squared. When you simplify that, you're going to get on top, 3 minus 2 is 1 squared, so that's a 1. This is negative 4 plus 1 squared, so that's a negative 3 squared, which is 9. So I get the square root of 10 right there. This one, 4 minus 6 is negative 2 squared, which is 4. This is 6 squared, which is 36, plus 4. This is the square root of 40. Now, how is that going to simplify? Well, down here, a 4 can come out. And when, because 40 is really 4 times 10, right? And so the square root of 4, so what this equals, the numerator is the square root of 10. The denominator, square root of 4 is 2 square root of 10. And those 2 square root of 10s cancel and you get 1/2. And there you go. So the sides are proportional. So you can say, yes, the triangles are similar because angles congruent and sides are proportional. Proportional. You can even say the similarity ratio is 2. All right. Last part. Can circles be similar? This would be a circle. This would be a circle. All right. The answer is yes. Circles are similar. All circles similar. All circles are similar. Let me put that word in there. All circles are similar. Why? Because, oh my, angles are congruent and the radius, or you can even talk about the diameters, are proportional. And we're going to get into that in a little bit when we get into circles. But just remember that all circles are similar. Another shape that are always similar are equilateral triangles, right? These sides are all equal, but what do all these angles measure? 60 degrees. These are all 60. So if I have a tiny little equilateral triangle, those sides don't equal these sides, but all their angles are still 60 degrees. Or if you have a huge equilateral triangle, all those sides are equal and all those angles are 60. So all equilateral triangles are similar to each other. Just like all squares would be similar, but not all rectangles. All right, that's the end of it.